At its core, all information storage faces the exact same physical problem, preserving distinguishable states against the constant degrading hum of thermal noise. To record a memory is to fight entropy, taking disorganized matter and snapping it into a protected, identifiable structure. For millennia, physics and biology alike have solved this through spatial encoding. We lock data in place by arranging matter in specific physical coordinates. From the exact sequence of base pairs in a DNA helix to the atomic spacing in a silicon chip, the information is protected by rigid physical architecture. The second solution is temporal encoding. Here, information is preserved as phase data within highly periodic oscillatory cycles, rather than fixed arrangements of matter. On the surface, a rigid carbon lattice and a pulsating atomic clock have absolutely nothing in common. One uses geometry to protect data in physical space. The other uses precise rhythms to protect data in time. Yet, if we look past the specific physical implementations, we find that both systems utilize the exact same underlying topological mechanism to isolate their information from environmental interference. The unified Chi-diamond model formalizes this connection. It proposes that spatial lattices and temporal oscillators are actually dual expressions of a single underlying physical property, a topological information capacity field. We quantify this field using a metric denoted as rho cap. This is a dimensionless, normalized measure of exactly how effectively a given structure, whether in space or in time, protects its distinguishable states from surrounding noise. By calculating these spatial and temporal capacities using mathematically symmetric descriptors, researchers have derived a generalized boundary called the information pressure law. This equation isolates the direct constraint between total information load, IP, and joint capacity, rho cap plus. This strict physical trade-off means a system cannot simultaneously maximize spatial density and temporal precision. This universal constraint defines the maximum amount of reliably retrievable data that can be packed into any given unit of spacetime, from silicon chips to quantum drives. To understand how rho cap operates, we start with the spatial archetype of memory protection, the face-centered cubic geometry of the diamond lattice. Each carbon atom bonds to exactly 4 neighbors in a tetrahedral coordination. In graph-theoretic terms, a coordination number of 4 is the exact mathematical minimum required for 3D structural stability, achieving the shortest possible total edge length while maximizing overall mechanical rigidity. This specific connectivity creates structural cages, closed loops of 6-member rings that adopt a highly stable cyclohexane chair geometry deep within the lattice. These geometric cages act as physical shields. Diamond achieves optimal spatial memory through the mathematical perfection of its topological isolation rather than simple atomic density. To rigorously quantify this spatial capacity across entirely different materials, simple structural counts, like counting the number of closed loops, are insufficient. Static counts ignore the presence of minor geometric fluctuations and noise. We solve this using a mathematical pipeline called persistent homology. This allows us to measure how robust a physical structure actually is as we shift our analytical length scales. This process involves constructing Vittori's-Rips complexes. We take a set of atomic coordinates and draw an expanding, overlapping sphere around every node simultaneously. As the scale parameter increases, the spheres begin to overlap. We draw mathematical edges where 2 spheres touch, solid triangles for triple overlaps, and complex tetrahedra for quadruple overlaps. Topological features emerge and vanish across this process. A physical loop is born at the exact scale when a ring of edges connects, and it dies at the scale where the expanding spheres finally overlap enough to completely fill the internal void. We map this data onto a persistence diagram. By charting the birth scale on the x-axis against the death scale on the y-axis, we plot the exact lifespan of every geometric loop in the material. Short-lived loops, caused by minor structural defects or thermal noise, cluster tightly against the diagonal line. But the structurally robust, lattice-level loops, the actual cages protecting our data, persist across many scales, appearing high on the y-axis. Spatial capacity, rho cap space, is defined by this exact persistence metric. It strictly rewards structural features that survive the coarse graining of physical dimensions. When we pivot to temporal encoding, the the physical medium changes entirely, but the mathematical goal remains identical. Instead of utilizing spatial coordinates, temporal memory organizes physical events to create protected, noise-free pockets in the dimension of time. The archetype for this is the time crystal, a state of matter first proposed by physicist Frank Wilczek in 2012. Continuous time crystals are defined by a ground state exhibiting spontaneous, robust periodic motion. In these systems, the periodicity is an intrinsic property of the matter's configuration rather than a response to an external drive. We also observe discrete time crystals, where periodically driven quantum systems lock into a subharmonic frequency. You pulse the system at one speed, and it responds stably at an exact integer multiple of that drive, maintaining a rigid temporal lattice for over 1 million cycles. This topological protection in time is not limited to quantum spin chains. We see it in the circadian rhythms of complex organisms and the vast population dynamics of biological microbiomes. The mammalian circadian clock and microbiome population dynamics maintain rhythms through a process called common filter fusion, which merges metabolic signals across scales from milliseconds to days. This hierarchy achieves a fractional frequency stability of 10 to the minus 12. By maintaining this precise periodicity against 300 Kelvin of thermal noise, these systems fulfill the criteria for biological or living time crystals. Preserving temporal memory relies on the precise same foundational robustness as spatial memory. It requires structural periodicity that remains completely stable against external noise. Just as spatial lattices are degraded by missing atoms or phonon vibrations, temporal memory is constantly destabilized by fractional frequency noise, representing constant short-time phase fluctuations that cause the rhythm to drift. To map this frequency noise, we analyze the system's power spectral density. This graph isolates exactly which frequencies carry stable periodic signals and which carry chaotic drift. High-quality oscillators actively suppress low-frequency flicker and random walk noise. By stripping away that interference, they compress their energy into ultra-narrow, highly coherent spectral peaks. We translate this raw spectral data into a metric known as Allen deviation. This allows us to quantify the oscillator's actual stability across varying intervals of observation time. Allen deviation functions as a filtered, scale-dependent summary of the clock's entire spectral structure, mathematically revealing the exact point at which the frequency noise overtakes the signal. This correlates directly to the concept of spectral persistence. Just as persistent homology tracks how well physical loops survive changing length scales, spectral persistence tracks which specific frequency peaks survive as our analytical time windows are progressively coarse-grained. Temporal capacity, rho cap of time, is the strict mathematical mirror to spatial homology. It measures exactly how well these periodic features survive the scaling of frequency windows. With these mathematically symmetric metrics established, we return to the unified information pressure law. We can map this law onto a two-axis constraint graph to visualize the absolute physical limitations of memory architecture. If we plot a high-purity NV diamond system, it achieves near-perfect spatial capacity. But its temporal stability drops almost to zero. Conversely, if we plot a hierarchical biological microbiome clock, it pushes the absolute limit of temporal precision, but its physical spatial structure is entirely fluid and disordered. The boundary curve connecting these extremes represents the absolute maximum joint capacity allowable by physics. The constraint is unavoidable. Pushing a design toward the spatial capacity of a diamond lattice forces a corresponding collapse in its temporal stability. In topological information theory, space and time function as conjugate variables. This perspective merges the engineering of physical structures with measuring temporal rhythms. However, the framework outlines a method to bypass the limitations of isolated platforms. It proposes a hybrid 4D memory architecture. This merges an NV diamond spatial lattice with the temporal modulation of a time crystal, executing time rondo patterns. We map temporal phases onto rigid spatial coordinates. Utilizing topological protections of both dimensions, this hybrid achieves a joint capacity orders of magnitude higher. This leaves us with a highly falsifiable prediction. Experimental physics should be able to measure strict, mathematically symmetrical relationships between spatial Betty number tests and temporal Allen deviation metrics. Defining spatial lattices and temporal oscillators within a unified topological framework provides the parameters needed for 4D memory architectures. This model establishes the physical boundaries for information storage by treating matter's geometry and event periodicity as a single dual capacity.